Okay, hello everyone. My name is Matthew Tsao, and today I'm going to talk to you about sample complexity of probabilistic roadmaps via epsilon nets. Motion planning is one of the most classic problems in robotics, and it entails finding a collision-free path from the start to the goal region. So for example, this is a candidate path that doesn't collide the black obstacles going from the start to the goal. Okay, now motion planning can be difficult when the state space is very complicated. And this happens when the robot has very complicated dynamics and when there's a lot of constraints that it has to satisfy. So in these settings, one very popular way of doing motion planning is called sampling-based motion planning. And I'm going to explain to you an algorithm called the probabilistic roadmap, or PRM algorithm, which is one way of doing sampling-based motion planning. So PRM approximates the state space using discretization, and it does this by randomly sampling states from the state space, which are these gray points, and then it connects any pair of gray points which are close by, and it is possible to move between them without collision. Okay, and once we have this graph, a path from the start to the goal can be obtained by running a graph traversal algorithm. Okay, so probabilistic roadmap has been studied extensively in the past, and the first studies of this algorithm were of the asymptotic flavor. So they showed that using random samples and a particular connection radius, as the number of samples goes to infinity, PRM will always find a path whose length is converging to the optimal path length. Okay, but interestingly, it was later showed that deterministic sampling is more efficient than randomized sampling. And this makes sense because random sampling, it might oversample certain locations and undersample other locations, whereas deterministic sampling aims to get a uniform coverage of the state space so you have good visibility everywhere. Okay, but we're not really interested in asymptotic results because we're never going to have an infinite number of samples, right? So what we really care about is finite sample results. And there are some settings, some works, which study random sampling behavior for PRM in the non-asymptotic regime. But if the asymptotic regime does tell us anything, it's that deterministic sampling is more effective. So what we want to do here is to provide a finite sample analysis of deterministic sampling algorithms for PRM. Okay? And this motivation largely stems from the desire to compute safe motion planning paths, right? So the observation is that safe paths are more robust against external disturbances and imperfect models. So here we've got two paths. One of them is shorter, but it also goes through a very narrow passageway and is more prone to collisions. And the longer one is sort of staying farther away from the obstacles, right? So it might be more favorable in certain situations. So to sort of state more formally, our objectives for this work are the following, right? So first we want to do the following. Given a motion planning problem, we want a test or an algorithm which will find a safe path in this problem if one exists. And if one does not exist, we want to be able to conclusively determine that no safe path exists. Once we do that, we want to understand how expensive such a test would be, right? So how many samples are needed for such a test to be accurate? And secondly, how many are sufficient? And once we have a sufficient sample size, what is the precise pattern of the sampling that will lead to the best result, right? So these are the things that we want to know. Okay, so to more formally state this as a mathematical problem, we'll need to define the notions of safety that we'll be considering. So we use clearance as our notion of safety, which just means the following. A motion planning problem is delta clear if there exists a solution where the state is never within delta of an obstacle, right? And so here the distance is measured with respect to Euclidean distance in the state space. Okay, so here is an example again. So the green path is delta clear, but the red one is not. Okay, so now that we have a definition for safety or via clearance, we're going to describe what we mean for an algorithm to be safe. So an algorithm is safe is going to mean it's complete. So a sampling algorithm is epsilon delta complete if for any delta clear motion planning problem, running PRM using the samples generated from this algorithm is guaranteed to find a solution with near optimal cost. Okay? So to sort of more mathematically restate our objective, we want to know how many samples are necessary or sufficient to achieve completeness as a function of the parameters epsilon and delta. Okay, so now we present the results. So we have a necessary condition. It says that in order for a sampling algorithm to be complete, for any epsilon, it must have sample size n and a connection radius r satisfying these inequalities, right? Okay, so the next thing we do is present a sufficient condition. So there is a sampling algorithm using sample size n and connection radius r, which is complete, and n and r have these forms. Okay, so if we look at this and compare it to the necessary condition, we see that the condition on the radius is basically the same for both of these. It only changes by a constant factor, so that's nice. We've characterized the optimal radius up to a constant factor, but the sample size, there's a bit of a gap, right? So the 2 is on the bottom in the denominator here, but in the sufficient conditions, it's in the numerator. So there's a bit of a gap, but the dependence on delta is the same for both, so that's nice. So what is the key idea behind these results? So the key idea leverages the properties of epsilon nets. So what is an epsilon net? Given a set S, we say that a set of points X is an epsilon net for S if for every point in S, there is a point in X which is very close to it. Okay, so for example, in this shape, we have these 6 yellow points. They form a net of this set, right? Because we can draw the balls around each of the yellow points, and that completely contains this set, which means that any point in this set is at least close to 1 of the yellow points. So that's what it means to be an epsilon net. And it's important when talking about deterministic sampling to discuss grids, because grids are very popular ways of doing deterministic sampling. And what we want to point out here is the following. Epsilon nets, as we saw over here, they cover the space with Euclidean balls, okay? Grids, on the other hand, you can think of them as covering the space with L infinity balls. And this distinction is important because a lot of motion planning algorithms and motion planning algorithm properties like connection radius and clearance, these are all defined in terms of Euclidean distance, right? So it stands to reason that epsilon nets, which are tailored for Euclidean distance, are more compatible with motion planning algorithms and concepts than grids, which are defined using the L infinity distance. And we formalize that here. So there is an epsilon net X, so that when you compare it with the grid of the same Euclidean coverage properties, the ratio of their cardinalities is small. Okay, that's what this says. And this might look a little weird, but one way to interpret this is the following. If epsilon is sufficiently small, then as the dimension grows, as for very high dimensional problems, the epsilon nets in general can provide the same coverage as grids while having significantly fewer points. And this is why we should be interested in them for the purposes of motion planning. Okay? So with the theoretical discussion out of the way, the next question is, can we use epsilon nets to get comparable coverage to grids while using fewer samples? So this is what we're going to discuss here. So the experimental setup is we're going to try to cover the d-dimensional cube of side length k with an approximate 1 net. And the reason we're using, a 1, sort of a radius 1 balls is because by rescaling, we can get, epsilon nets for any epsilon, okay? So that's why. We're going to measure the size of the set we get and compare it to the size of an equivalent grid. So that's going to be the ratio rho is going to be the number of points in our set divided by the number of points in the grid. And then see what fraction of the space is uncovered, right? So this should be small if our algorithm is good. And what we see here is that, so what we see here is for high dimensions, the number of fraction, the fraction of points we use compared to the grid is very small, and the fraction of the space that is uncovered is also very small. So what this basically means is that for large dimensions, epsilon net based sampling achieves nearly the same coverage as grids while having significantly fewer samples. So to summarize, we introduced a concept of completeness that can be used to find paths of high clearance. We then studied the sample complexity of complete algorithms, like how many samples are necessary and sufficient. We then discussed why epsilon nets may be more compatible with Euclidean algorithms than grids, and we showed that epsilon nets can lead to more efficient sampling than grids empirically as well.